here's a chemistry example. So pressure, capital P, and volume, capital V, and temperature, capital T. I guess I should give some units if you really want units. I don't really care about units. Pressure in kilopascals. That's something I talk about all the time. Volume in liters. Okay, that makes more sense. And temperature in kelvins. So pressure, volume, and temperature of 1 mole of an ideal gas are related by the ideal gas law. PV equals, I always heard it like PV equals nRT. I guess nR is about 8.31. Right, that's, I mean, I imagine a lot of you have heard PV equals nRT, like, but nR are just constants. Their product is apparently approximately 8.31. So here's what we're going to ask. If the temperature of a gas is 300 degrees Kelvin and increasing at a rate of 0.1 per second, and the volume is 100 liters and increasing at 0.2 liters per second, how fast is the pressure changing? Excellent question. How fast is the pressure changing? So for this, we need the chain rule. Well, I should say, we have to first think about how this is a function of two variables, right? So we're going to isolate the thing that we're talking about. We're going to say, all right, I'm going to say that pressure is going to be 8.31. Instead of doing temperature divided by volume, I'm going to make it easier to differentiate this in the future and just write it's 8.31 times T times V to the negative first. That seems like a way better route to take so that it's going to be easier for you to differentiate things. So whenever you are trying to kind of differentiate something that's a function of a couple variables, and those are also functions of other things, we have to kind of set up this map. And so what I would point out here is that everything here is a function of time. And temperature and volume are changing as time goes on, right? Specifically, the temperature is increasing at 0.1 Kelvin per second, and the volume is increasing at 0.2 liters per second. Those both depend on time. I don't really want to write out an equation for them, but if you really wanted to, you really don't want to, but you can really say, okay, the temperature is going to be, it's starting at 300, and we are adding 0.1 kelvins every second. So time is measured in seconds, that would be your temperature equation. And if volume is measured in liters, here's your volume equation. We don't need that at all, but you could write those equations if you really wanted to. The point I want you to see, though, is that pressure is a function of temperature and volume. And temperature, and volume are both functions of time. And this is the kind of map that you want to set up whenever you're trying to do some sort of chain rule differentiation thing, where you've got something as a function of multiple variables, and that those variables are functions of some other variables. It's a very, very common thing to do. This is exactly the kind of thing we're going to be doing for problem 1 on your homework, or a similar problem to the problem on your homework. It just got a little bit more machinery built up. So here's what I'm trying to find. Well, in fact, let's go back to the question. The question is, how fast is the pressure changing? So what I'm really trying to find is, what's dP dt? What's the rate of change of pressure with respect to time? how fast is pressure changing as time is changing. To find that, we have to find all of the paths that get you from pressure to time. How many paths are there? 2. I can go that way, go through temperature, or I can go that way and go through volume. And so on these paths, when I go from pressure to temperature, I'm taking the derivative of pressure with respect to temperature. And when I go from temperature to time, I'm taking the derivative of temperature with respect to time. So when I travel down this path, each little leg of the path is a derivative. So derivative of pressure with respect to time is going to equal, I've got this path, del P del T times dt dt. Del is because pressure is a function of 2 variables, so I'm taking partial derivatives there. D is because temperature is a function of just 1 variable. Sorry, you can't see that. Thank you. So just say the words. If I like say something, if I'm not getting it. And D because temperature is a function of just 1 variable time. And then I have to add on the other path. Okay, it's going to be del P del V times dV dt. I will point out, if you screw up the del versus d part, no one's probably really going to care that much. But it is worth noting, we use del when it's a function of more than 1 variable to indicate a partial derivative. We use d when it's a function of 1 variable to indicate a regular derivative. Okay. And right, here's path 1. Here's path 2. And then we're going to plug in what we know. I should look back here. So here's what we know. They told us that the rate of the temperature is increasing at a rate of 0.1 Kelvin per second. So I know that the temperature rate of change is 0.1. I could write the units, I suppose. I usually kind of don't worry about the units. I also know that the rate of change of volume is 0.2 liters per second. But I guess I'm going to need to find this thing here and this thing here. Luckily, I know what pressure is as a function of time and volume. So del P del T is going to be 8.31 times V to the negative 1. Or if you prefer, 8.31 over V. I don't really prefer. Del P del V is going to be 8.31 times T. And the derivative of V to the negative 1 is negative V to the negative 2. So putting it all into my equation here, d P dt is going to be del P del T, which is 8.31 times V to the minus 1, times del T, which is 0.1, plus del P del V, which is gnarly looking, 8.31. I should really write a minus 8.31 times T times V to the minus 2 times the dV dt, which is 0.2. And then I'm going to plug in T equal to 300 kelvins, was it? Yeah, 300 kelvins. And volume equal to 100 liters. So I'm going to get something gnarly. I'm going to get dP dt equal to, okay. Interesting there. Yeah, okay, that's fine. I'm going to get, let's see, that's going to be 8.31 times 100 to the negative 1, or 8.31 over 100 times 0.1 minus 8.31 times T, which is 300, times 100 to the negative second, or divided by 100 squared, times 0.2. This is definitely the time to use a calculator. No one is calculating this by hand. Don't be ridiculous. When we do this, we're going to get about negative 0.04155. What are my units? Well, I'm talking about the change in pressure and the change in time. I know my time units was what? Hours, minutes, seconds. My time unit was seconds. Can I see your symptom survey, please? And what was my measurement for the unit of pressure? It was terrible. It's something I never even think about, really. It's kilopascals. Okay. Kilopascals. All right. So the numbers, not so important here. The idea is super important. We write our function as a function of its variables, and then those variables as functions of what they're a function of. So we kind of make this path where each level down is kind of the next thing that the previous thing is a function of. Questions about this? We're going to do more, don't worry, but are there questions about this? Okay. Don't worry, we're getting to a similar question to your homework one, but I want to do a couple examples before we get there, because that one's just a little bit worded kind of weirdly. Let's look at another example. Suppose f of xy equals x squared e to the 3y. And sure, x is cosine of t, y is sine of t. You can come up and show me. So we want to find df dt. Thank you so much. I want to find df dt. And there's actually a couple ways you can do this. Here, we could totally do it the quote unquote long way. We could write, well, f as a function of time is f of cosine of t, sine of t, right? Just replacing x and y with what they're equal to. And that's going to be cosine of t squared times e to the 3 sine of t. And we can take the derivative of this. It's not going to be pretty, but it can be done. F prime of t is going to be, I guess I can write df dt. Let's see, product rule, chain rule, all that stuff. The derivative of cosine squared is 2 times cosine of t to the first times the derivative of cosine, which is negative sine, times the other stuff left alone. I'm using the product rule. So there's, right, that's the derivative of cosine of t squared. And then we're going to add, and we're going to do the opposite. We're going to leave the cosine of t squared alone and multiply by the derivative of this. And the derivative of e to the stuff is e to the stuff times the derivative of the stuff. And the derivative of the stuff is 3 cosine t. And I don't really think we should simplify that unless someone really wanted us to. No one wants us to at this point. Let's see what I think of as a better way. So this is fine if you can do it this way, right? But it's not always relatively easy to maybe plug in what x and y are. Sometimes we don't know. So this is an option, but it's more of an option just to see that the way we're actually going to do it produces the same result. So the other way is to do the path thing. I don't know if there's, I mean, it is the chain rule, but we draw this little path diagram. So f is a function of x and y, and both x and y are functions of t. So again, there's going to be two paths. And df dt is going to equal del f del x times del x, sorry, dx dt plus del f del y times dy dt. So let's see what we get. Oh, sorry, things are a little crooked there. Okay. So looking at our original function, del f del x is just 2x times e to the 3y. dx dt is negative sine of t. And then del f del y is, well, the derivative with respect to y is x squared times e to the 3y times 3. And then dy dt is cosine of t. Are these the same? I mean, not exactly. They don't look the same because they didn't plug in what x and y were. But you can see that if I plugged in x equal to cosine and y equal to sine, I'd have exactly 2 times cosine times negative sine times e to the 3 sine. Sorry, you can't see some covering up with my big hands. And then you'd have cosine squared times e to the 3 sine times 3 cosine. Same exact thing, just not written all the way out. And typically, we view this second way of doing it as much more simple, right? It was way easier to do this and then plug in the stuff if we need to after that. How is cosine t squared? Like in the original, like, let me ask you, right here. Oh, I forgot to put my picture in the thing. I mean, not that it's super important, but I always feel like the video is weird if I don't put the picture in there. There we go. I'm not sure. Can you clarify? Like, I'm not sure where you're asking about the cosine squared. Under line 1, the partial derivative of cosine t squared. So the derivative. So when I take the derivative of something squared, I'm using the chain rule. The derivative of x squared is 2x. The derivative of cosine squared is 2 times cosine to the first. But then you have to use the chain rule and multiply by the derivative of cosine, which is negative sine of t. So that's what's happening there. We're using the chain rule. You can also use the product rule if you want to make it more complicated and say it's cosine times cosine, but you shouldn't do it that way. You should use the chain rule. Okay. So let's go ahead. So let's look at something that I made up that's similar to your homework problem, but not exactly the same. So the issue with your, well, in fact, let's actually go back for just 1 second. The issue with your homework problem essentially really is, and we'll cover this in a moment, you don't know what this is, right? You don't have that. They don't give you the function. They give you the derivative with respect to x and the derivative with respect to y. Although, if you think about it a little bit, you could probably reconstitute the original function in there. It's not too hard to think about. It's almost right there for you. I'm not going to tell you right now. But what I want to point out is to find the derivative of this composition, we don't actually need to know the original function. To find the derivative of the composition, all you need to know is del f del x, which are totally being given, times dx dt, which we can definitely find, plus del f del y, which were again being given in the homework problem, times dy dt. Now, I know I've said it like it's supposed to be easy or something, but it's still a lot of, like, he's giving a lot of just stuff here. So let me try to translate a little bit. So here is my made up function. Let f be a function from R2 to R. All that means is you've got f of a function of f is a function of 2 variables, and it's giving you 1 output. I'm going to tell you the function, but we're going to all pretend like we don't know what it is. So the function we're going to use is f of x, y is x cubed times y to the 4th. That might be a terrible choice. I don't know. We'll see. And so this is a function such that here's the information we're actually being given. The partial with respect to x, del f del x is going to be 3x squared y to the 4th, and del f del y is x cubed times 4y cubed. So we're pretending like we don't know this information in red because we don't need it actually. All right, now here's where things get a little bit weird, I feel like, in this setup. Let G, I can't draw a bold-face G. I'm not that talented, so I draw it with an arrow and it's a vector valued function. This is kind of funky. I don't think this is particularly necessary. Let G be a vector valued function that takes an input and gives an output of an ordered pair. Yeah. Isn't it? I know. Does the order of multiplication matter? So I agree with what you're saying. You're totally right. The derivative is 4y cubed times x cubed. But what I'm doing is I'm just putting the 4 in front. Yeah. Okay. So this is just saying you have an input and your output is an ordered pair. And I've made up, in this particular case, G of t is e to the 2t comma tangent of t. Now, here's where I feel like things get really bizarre. We're going to say that h of t is f of g of t, and we want to determine dh dt evaluated at t, which seems especially strange that you're saying evaluated at t, but whatever. Okay. So here's what I'm seeing. I'm seeing f is a function of what variables? At the very kind of basic level. That was maybe not the best question. Looking at this information here, f is a function of what variables? Right. Bless you. Now, it's maybe harder to see what are x and y both functions of. Well, it's not super clear. It's in fact, it's maybe not even really true. I want to say that x and y are both functions of t. And if I'm thinking of f of g of t, well, then it is kind of true, because what I'm going to be doing is I'm going to be saying that if I actually went here, right, I would be plugging in g of t, which is this for x and this for y. So again, here's some information we don't really know, but I'm going to show you anyway. F of g of t would be f of this ordered pair, e to the 2t tangent of t, and that would be equal to garbage. It'd be equal to e to the 2t cubed times tangent of t to the 4th. But what's important to see here is that the way we are setting this up means we're saying f is a function of x and y are both functions of t, so that we're really writing f as a function of t, or h as a function of t. But again, I admit it's kind of weird because nowhere on this homework assignment does it ever say x and y depend on t. Right? I mean, I'm looking at it right here. Nope, never says that. But the idea here is that in the spot that x and y would go, we are plugging in the first part of the function of t and the second part of the function of t. We're plugging in this for x and this for y. So x and y do depend on t because we make them. And now we've got our map. And we can find df dt, which you could also say is dh dt, which I know might feel weird, but h and f are really the same thing. It's annoying. But I'm going to say df dt is del f del x times dx dt plus del f del y times dy dt. And look, I have all of that information. Del f del x, they gave it to me. How kind. Del f del x is 3x squared y to the 4th. What's dx dt? Well, what's x? right? X is the first coordinate that we're inputting. So X as a function of time is, or T, is e to the 2t, and dx dt is going to be 2e to the 2t. Plus, what's del f del y? They gave it to us. It's 4x cubed y cubed. And somebody please tell me, what's dy dt? What's the derivative of tangent? Well, everybody should be able to tell me this. The derivative, so the derivative of tangent is not arctangent. It's a good guess. It's another trig function. Yeah, it's another trig function squared. It's secant squared of t. Exactly. Oh man, sorry. My wife was just telling me that I accidentally trapped our cat in another bedroom and left the door closed. I feel kind of bad about it. She's okay. She's alive. Just I feel guilty. And she probably, yeah. Hopefully she didn't like do anything terrible in there. All right. So anyway, our cats are old. Sometimes they don't always act the way we'd like them to. Anyway, back to the math. We're almost done, except we're asked to write this as a function of t. We don't want x's or y's. So we have to replace every x and every y with what it's equal to. So x has to be replaced by e to the 2t. Y has to be replaced by tangent t. This is going to equal 3 e to the 2t squared tangent to the 4th of t times 2e to the 2t plus, I'm going to write in the next line so I have enough room, 4 times e to the 2t cubed times tangent cubed times secant squared of t. Sorry, one sec. So that's the idea. And you can definitely approach problem 1 from your homework in a very, very similar way. Notice, I never actually had to use the fact that the function was equal to x cubed y to the 4th. Right? We could have, but we never needed to. It was helpful to kind of know that if you plugged in this for that, right? You could totally, right, write the function this way if you really wanted to, as e to the 2t cubed times tangent of t to the 4th. And then if you took the derivative of this, you would get all of that, right? Something cubed is 3 times something squared times the derivative of that something times the other part from the chain rule, product rule. And then do it the other way. The derivative of tangent to the 4th is 4 times tangent cubed times the derivative of tangent and then times the other stuff. It's all there. So that's how you would approach that problem. It's not a terrible question. It's just a little bit hard to comprehend because it's really, I feel like this part's kind of the unclear part. Like g is a function of t, but really those things are what x and y are supposed to each be. That's kind of the piece I feel was difficult to kind of parse out. I mean, it's not the only difficult part. It's like the furthest. Yeah.
What was the purpose of h of t?
That's a good question. Yeah, I don't know, because I would have just written it. I mean, I guess the purpose there is that it's not maybe correct to just write f as a function of t, because it's not. It's a function of x and y, which are then functions of t. So the idea here, I guess, is that it makes more sense maybe to write h as a function of t, because then you can talk about its derivative kind of more directly. Yeah, I don't think what I'm saying is particularly great about that, but that's the best I've got. Yeah, I guess because it's probably not super, like writing this might not really be excellent, but it's not that bad either. So that's what I'll say about that. Other questions? Okay, let's do a little more chain rule, and then we'll talk about some directional derivatives. Unless there's something else you guys are burning with desire to know about. Really, I will just point out, oh, sorry, this question here. Oh, we got it, okay, cool. You certainly, especially all of you being in the same class, right? You are welcome to direct the flow of things. If there's something that I'm missing that is going on in class, you should speak up because you're the only class I'm here to serve, right? It's not like there's 4 different 17C classes. There is one 17C class. So if there are things you need to hear about, let me know. But chain rule is what's on deck. So let's do 1 or 2 more. Just take a look real quick. Oh, another step. Yeah, let's say we have this lovely looking thing. W is a function of x, y, and z is equal to x e to the y squared z. Yes, of course. And let me also do the thing that makes it so you can see more of the screen. That would be great. Yeah. So to find g of t, we would just plug g of t values into t. So we're not really finding g of t, we're finding f of g of t, but we're not actually doing that. We don't actually know what the function f is. What we're really doing is we're saying, well, we know that g of t gives us these 2 things, and then the first coordinate is what gets to act like the x, and the second coordinate is what gets to act like the y. Because when we do f of g of t, we're doing f of e to the 2t tangent of t. So that gets to act like your x thing, and that gets to act like your y thing. That's what's going on there. But again, right, this is the part that feels a little dicey because like you don't actually have the function f. So it feels weird to be using the partials without having the function, but that's what we're doing here. That's why we're really using this to be like, okay, we know all these pieces so we can get what we want. I will mention, if it helps you see things, the function that your actual homework problem is coming from, where the first partial, the partial with respect to x is y e to the xy, and the partial with respect to x, starting with y, is x e to the xy. This function here is just e to the xy. If you take the partials, you can totally see it. You don't need that piece of information, but if it helps you work things out, it's worth looking at. So let's look at this. We've got w as a function of x, y, and z. And then we also are going to have x, y, and z all functions of t. X is t squared, y is 3 minus t, z is 5 plus 2t. And I want to find dw dt. And if I were a student, I get really good at making that symbol look like it could either be d or del. I mean, I'm just saying. Is that a d? Is that a del? I don't know. It could be either. It could be whatever I need it to be. I mean, it's a d. But if I were a student, I might try to skirt the line there. So I need my little path. W is a function of x, y, and z. And all of x, y, and z are functions of t. So I'm going to have 3 paths. I'm going to have del w del x times dw dt plus del w del y times dy dt plus del w del z times dz dt. And then we just take a lot of derivatives. Del w del x is going to be e to the y squared z. Or I could really say 1 times e to the y squared z times dw dt is, that doesn't look right. It doesn't look right. Specifically, let me point out these other ones. I know they're not fractions, but if I could cancel things like they were fractions, what would cancel in this first one? The dy or the del y, whichever thing you want to call it. And I'd be left with what? Right. How about here? Same deal. DZs would cancel. I'd be left with dw over dt. This notation is picked purposefully. Right? It's meant to look like that. It's meant to look like if you could cancel the fractions, you would get what you wanted to get. That's not right. Nothing's canceling, first of all. What should I actually have here? Not dw dt. I need a dx dt. Right? Because I should have been w to x is del w del x, and x to t is dx dt. So dx dt is going to be 2t plus del w del y is going to be, all right, so I've got a constant times the derivative of e to the stuff is e to the stuff times the derivative of the stuff with respect to y, which is 2yz, times del y, sorry, dy dt, which is -1, plus del w del z, which is going to be, again, the constant x times the derivative of e to the stuff is e to the stuff, times the derivative of the stuff, and the derivative of y squared z is just y squared, times del z del t, which is going to be 2. And I don't want to do any more of that. But if they said something like, write this as a function of t, then you have to go and plug in all the things that y and x and z are equal to in terms of t. So we could write this as, I'm not going to do the whole thing, but it would be e to the 3 minus t squared times 5 plus 2t times 2t plus t squared times ... You get the idea, I hope. All right, you guys get the idea? I don't need to do the rest. Okay, cool. I'm not giving you the chance to say yes. But that's it, right? If you needed to write it as a function of t, you totally could just plug in what x, y, and z are equal to in terms of t. Let's do one more. Yeah, one more. Because sometimes they get a little bit more interesting. Yeah, more interesting. Yeah, more interesting. So let's say we have the following. Let's say we had our function of x comma y, or sometimes we just call it z. Let's say that that's equal to the inverse tangent of x plus 3y. Or if you prefer, you could alternatively call it the arc tangent of x plus 3y. Did your teacher have a preference? Has he talked about inverse tangent or arc tangent? Okay. Either way is fine. I like the arc tangent because it eliminates the possibility of making the mistake of thinking that this is 1 over tangent, right? It's not 1 over tangent. 1 over tangent is cotangent, and cotangent is definitely not the same thing as arctangent. So in case it was unclear, this is definitely not 1 over tangent. Very, very different things. I can say more about that if you would like me to, but I won't if you don't want me to. And then we're also going to say that x is a function of s and t. S is never my favorite variable to use. S squared times t, and y is going to be s times the natural log of t. Okay. I don't like s because s is always end up looking like 5s, or vice versa. And we want to find, let's find del z del s. Let's do both. Who am I kidding? Del z del s and del z del t. And notice that I'm writing del because at the very lowest level, z is a function of s and t. So when I find the derivative with respect to s, it's a partial derivative. With respect to t, it's a partial derivative. I'm still doing the same thing. I'm still making some paths. So z depends on, at the highest level, x and y. And then x and y depend on, well, each of x and y depend on both s and t. So x depends on s, and so does y. And x depends on t, and so does y. So there's a lot of paths to get to either one. So if I want to find del z del s, and you can find all the paths to s. So let's see here. I'm going to go this way and then this way. And I'm going to go this way and then this way. So that's going to be, let's see, del z del x times del x del s plus del z del y times del y del s. And then we do the things. Oh, what's the derivative of inverse tangent? Or arctangent. So d dx of arctangent of x is what? And that's been a while. 1 over 1 plus x squared. So the derivative of arctangent of x is 1 over 1 plus x squared. The derivative of arctangent of some stuff is 1 over 1 plus the stuff squared times the derivative of the stuff. Because chain rule. So this is going to be derivative with respect to x. So it's going to be 1 over 1 plus the stuff squared times the derivative of the stuff, which is what? What's the derivative of that stuff? I heard one person kind of say it quietly. Yeah, it's 1 times del x del s, which is going to be 2s times t. Plus, then we'll do it for y. So del z del y is going to be, again, the derivative of the arctangents and stuff is 1 over 1 plus the stuff squared. But now everybody should be able to tell me what am I going to multiply by this time instead of 1. Why did I multiply by 1 last time? Because it was the derivative of x plus 3y. Thank you. Yeah, I'm going to multiply by 3 because it's the derivative of x plus 3y with respect to y instead of with respect to x. And then, hopefully I have enough room here. We're going to multiply by del y del s, which will be the natural log of t. And then if you wanted to write it as a function of just s and t, you could plug in what x, y were equal to. No one's usually asking you to do that, though. And it's not really the point. And then in a similar way, you can find del z del t as del z del x times del x del t plus del z del y times del y del t. The nice thing about this thing is we've already done half of it. We've already gotten, right, this piece is still the same, this piece is still the same. It's the partials at the end that are different. So it's just going to be still 1 over 1 plus x plus 3y quantity squared times 1. But now times, right, we've done that first part of the path, but now we're going this way. And del x del t is going to be s squared plus del z del y didn't change. It's still 1 over 1 plus x plus 3y quantity squared times 3 times, now what's the derivative of y with respect to t? That one more time. You're most of the way there. What else do we need? The s, right? Because the s is a constant multiple that's going to hang out. So it's really going to be s times 1 over t or s over t. And that's it. Has your instructor, professor, whatever his title is, talked about the chain rule as a shortcut for implicit differentiation? Okay. If he does, let me know. We'll talk about it. Also, I should mention, you're certainly welcome to take pictures of anything you want. I do post the notes on the Google Drive. It's linked from Canvas. So while you're certainly welcome to take a picture of these notes, it's probably easier to see them later on when I upload them. But again, whatever you want, fine. Just want to let you know they are available to you in a place where it's easier to access them. Okay, so not that. Not that. Not that. Yeah. There's a lot of that. Okay. Yeah, done with that. Cool. Directional derivatives. Can I get my thumbs to work? Maybe. Okay. There was something I wanted to say. All right. So something we need to know for directional derivatives is the dot product. So if we've got two vectors, let's call them u and v, and there's an angle between them, we'll call it theta. Then if we want to find the dot product of u and v, now a couple of things to know when you're taking the dot product is a way of quote unquote multiplying vectors together. There's also something called the cross product, which did you guys talk about last quarter in 17b? Yeah, okay. I don't think we use the cross product really in this quarter at all, but I could be mistaken. The dot product is a way of multiplying two vectors together in a way that gives you a real number as an output. Right? Our inputs are vectors, two vectors. Our output is some scalar value. And one way of doing this, which is not the way we're probably going to do it most of the time, is it's the magnitude of the vector u times the magnitude of the vector v. Magnitude is just another word for length, times cosine of the angle between them. I don't think we really use that as much here, but a couple of things to be aware of. One thing in particular, if the dot product of two vectors is equal to 0, well, assuming neither of them is the 0 vector, because the 0 vector is just kind of boring, that means the magnitude of each of these is non-zero if they're not the 0 vector. So the only way that this product is equal to 0 is if cosine is equal to 0. And what angle does cosine of equal 0? 90 degrees, or in radians? Yeah. So if the dot product is 0, we automatically know that the angle is pi over 2 radians, or 90 degrees. Or more generally, we say that u and v are perpendicular. So if you ever are told that the dot product of two vectors is 0, you're like, oh, those vectors are perpendicular to each other, or orthogonal to each other is another word we use to mean the same thing. In practice, though, if you want to take the dot product of two vectors, and there's probably like 3 good ways of writing vectors. One way I like to write them is with this. Yeah, sure. I'm more partial to this, to be honest. I like to write my vectors as column matrices, but someone else might write it as something like that. Someone might write it as parentheses. I mean, I apologize. There are so many ways of writing this. Someone might use slanty brackets. All these are perfectly good ways of writing the vector u. So just be aware. Hopefully, this one's kind of the worst option in my opinion, because there are other things we use that notation for. So if I'm writing u like this, and v as the coordinates v1 and v2, then the dot product of u and v, which is going to be the dot product of the vector u1, v2, and the vector v1, v2. The dot product is really easy to calculate if you know the components of the vector. It's just the first components multiplied together, added to the second components multiplied together. That's it. So for example, if u is equal to the vector 3, 4, and v is equal to the vector 5, -2, then the dot product of u and v is just 3 times 5 plus 4 times -2, which is 15 minus 8, which is 7. There's something I want to say about that. There really is something I want to say about that. Oh, I know what it is. Gosh. Oh. You guys have talked about vectors a little bit in this class. He's talked about the dot product. Yes, no, no. So when you guys find out, I will certainly write vectors the way that he's writing them, if that makes sense, if he's doing it one particular way. This is what I'll do for now, but if you are like James, he's writing them like this, or like this, or like this, just let me know and I will switch it up, because I don't really care which way I have to write them. I know that I knew there's one other way we could write them. You could also write this vector as 3i plus 4j, and this vector as 5i minus 2j. That notation is really just where we are saying I is the unit vector in the x direction, if you want to write it that way. And j is the unit vector in the y direction. And so u being the vector 3, 4 is really just 3 times 1, 0 plus 4 times 0, 1, which is 3i plus 4j. And sometimes people throw some arrows on top of those. Sometimes they don't. It doesn't really matter either way. So that's a pretty typical way. Gosh, why am I so like off kilter here? Sorry. That's a pretty typical way of writing vectors as well. Again, whatever we want to do in class, fine with me. But there's a lot of different ways to do it. So I definitely saw some directional derivative questions on people's homework, right? I'm not crazy. Yeah, there's definitely there. But what I'm hearing is he hasn't talked about it yet. Is that correct? Has he talked about the directional derivative? Kind of. Okay. How much time have I got? Okay. Yeah, we're gonna do the long thing. Okay. So why does the directional derivative work the way it does? Well, for that's gonna take a little bit of building up. You probably don't want to write this next part down. That doesn't mean you can't, just that if you want to take a break from writing